Now welcome back to one-dimensional flows, where we are still dealing with flows on the line. The focus of this lecture will be on fixed points and stability. Now the geometric way of thinking can readily be applied to any one-dimensional system. X dot is equal to f of x. Now essentially we just need to draw the graph of f of x and sketch the vector field on the real line. So just as an example, x dot versus x, and you plot any arbitrary function f of x, where we highlight the fixed points of the system and draw the direction of the flows. Now what we do is you place an imaginary particle, which is called a phase point, at x naught and see how it is actually carried by the flow. Now as time moves on, the phase point moves along the x-axis according to some function x of t. Now this function is called the trajectory based at x naught and represents the solution of the ordinary differential equation starting from the initial condition x naught. The above picture, which shows all the qualitatively different trajectories of the system, is called a phase portrait. The fixed points x star defined by f of x star is equal to 0 correspond to stagnation points of the flow. The solid dot is a stable fixed point, and the local flow is towards this stable fixed point. The open dot is an unstable fixed point, and the local flow is away from it. In terms of the ordinary differential equation, fixed points represent equilibrium solutions. If initially x is equal to x star, then x of t is equal to x star for all t. And equilibrium is stable if all sufficiently small disturbances away from it actually damp out in time. Unstable equilibria, in which disturbances grow in time, are represented by unstable fixed points. Now let's consider some examples. We've talked about some theory, and let's look at some examples now. So find the fixed points for x dot is equal to x squared minus 1 and classify the stability of those fixed points. So x dot is equal to f of x, which is equal to x squared minus 1, which is equal to x minus 1 times x plus 1. So to find all the fixed points, we set f of x star is equal to 0 and solve for x star. This gives x star is equal to plus 1 and minus 1. The algebra is straightforward. Now we need to determine if these fixed points are actually stable or unstable. So we have to plot x squared minus 1 and sketch the resulting vector field. So we go ahead and plot x dot versus x and make a plot of f of x is equal to x squared minus 1. Highlight the direction of the flows and highlight the fixed points. The flow is to the right where x squared minus 1 is greater than 0, and to the left where x squared minus 1 is less than 0. Thus x star is equal to minus 1 is a stable fixed point, and x star is equal to 1 is an unstable fixed point. Now we go ahead and highlight the stable fixed point and the unstable fixed point in the diagram. Now here's a question for you. Can you actually find an explicit analytical solution to the above ordinary differential equation? Now note that we have been able to classify the stability of the fixed points without actually knowing the analytical solution. But do go ahead and try and see if you can find an explicit analytical solution to the above ODE. Now here are some notes. The definition of stable equilibrium is actually based on the notion of small disturbances. So small disturbances to x star is equal to minus 1 will actually decay. A large disturbance where x finds itself to the right of x is equal to 1 will actually not decay. In fact, the phase point will get repelled towards plus infinity. To get this point across, x star is equal to minus 1 is locally stable but not globally stable, in the sense that we will not have convergence from any arbitrary initial condition. Now let's consider another example. Consider the equation x dot is equal to x minus cos x. Sketch the phase portrait and determine the stability of the fixed points. Now let's plot y is equal to x and y is equal to cos x. Now that's a curve for y is equal to x, and that's a simple-minded curve for y is equal to cos x. Now note that they intersect only at one point. The intersection is a fixed point since x star is equal to cos x star, and therefore f of x star is equal to 0. When the line is above the cosine curve, then x is greater than cos x and x dot is greater than 0, and so the flow is to the right. When the line is below the cosine curve, then x dot is less than 0 and the flow is to the left. Now we go ahead and actually identify the fixed point x star. Now x star is the only fixed point and it is unstable. Now we do not have a formula for x star, but we were still able to classify its stability. Now let's look at our final example and consider an electrical circuit. So let's go ahead and actually make a diagram of our electrical circuit. So we have a resistor R and a capacitor C, which are in series with a battery of constant DC voltage V0. Now suppose that the switch is closed at t is equal to 0 and that there is no charge initially on the capacitor. Let Q sub t denote the charge on the capacitor at t greater than or equal to 0. Then let us try and understand some aspects of this particular system. Now, this type of circuit is actually governed by linear differential equations and can actually be solved analytically. However, we work with a geometric approach to try and get some intuition about the above circuit. So now if you go around the circuit, the total voltage drop must equal 0, which gives us minus V naught plus Ri plus Q divided by C is equal to 0, where I is the current flowing through the resistor. The current causes the charge to accumulate on the capacitor at a rate Q dot is equal to I. This gives us minus V naught plus R Q dot plus Q divided by C is equal to 0. Rewriting this, we get Q dot is equal to F as a function of Q is equal to V naught divided by R minus Q divided by RC. Now the graph of F of Q is just a straight line with a negative slope. Now that's the plot of Q dot versus Q, and we plot F of Q on this plot. The vector field has a fixed point where F of Q is equal to 0 at Q star is equal to C V naught. So we highlight the fixed point. The flow to the right where F of Q is greater than 0, and the flow is to the left where F of Q is less than 0. So the flow is towards Q star, and hence we have a stable fixed point. Now let's plot Q sub t versus t. Start a phase point at the origin of the figure, and let us imagine how it would move. The flow would carry the phase point monotonically towards the fixed point Q star. The speed Q dot decreases linearly as it approaches Q star. So Q sub t is increasing and concave down. Now let's go ahead and plot Q sub t versus t and highlight the equilibrium value Q star and denote the stable fixed point. And that's the curve for Q sub t versus t. Now in fact, the fixed point is approached from all initial conditions, and so in that sense it is actually globally stable. Okay, so let's have some final comments and remarks about this lecture. Now this lecture was centered around fixed points and stability, and we started dealing with stability in a little bit more detail because stability is a key concept in the study of control and nonlinear dynamics. Now we had these special points referred to as fixed points, and we were able to classify whether the fixed points were stable or they were unstable, and we were able to do this without any formal algebraic technique. But there was one point of subtlety that arose, and that was of local versus global stability. Now let's just sort of take an example. So for example, you've got this pen of mine, and let's assume that the tip of the pen is a stable fixed point. So if I found myself to be in an epsilon neighborhood of this stable fixed point, then there's a decent chance that I would actually get attracted towards that stable fixed point. On the other hand, if there was a large disturbance and I found myself rather far away from this particular stable fixed point, then it isn't very clear that the trajectories would actually converge towards the stable fixed point. In fact, one of our examples highlighted that you could actually diverge away from that stable fixed point if you actually had a large disturbance. So there's one subtle point which came out in the lecture, and that was of local versus global stability, and that should be one of the key takeaways from this lecture.